Welcome everybody. Welcome to Decarb 101 put on by the Young Professionals Group. I'm Chase Davis. With me is also Chase Doobie with co-chases of the Young Professionals Group for IDEA. So one of the focuses that we've had with the YPG group is really to try to increase engagement with the district energy professionals, but really targeted the ones that are kind of early on in their careers. One of the best ways we found to do that is really to give people kind of that first push into certain topics, entry-level education or higher level education about what it is district energy does. Recall we had done this with IDA 101 hosted by Rob Thornton, who had kind of given an overview of what IDA does as an organization. Also had Juan Tiveras, who did this for kind of District Energy 101, sharing his experience really from a broader range of topics, not always getting deep down into the nitty gritties like a lot of the technical seminars do. So it's really in that spirit that we decided we want to take that approach with one of the hotter topics in district energy right now, which is decarbonization. And I know everyone's probably starting to deal with this in certain facets, some people more than others based on locale or their own political or otherwise pressures with organizations they work with. But it is a topic that's big right now. It's something that everyone's looking to get into. So before we kind of launch this, I'll turn it over to Chase Dewey's go through a couple of housekeeping slides and introduce Martha.
So as we all adjust to virtual meetings that we enjoy every week, we need to remember professional etiquette of making sure your mic is muted. For this presentation, it's more of a webinar, so you don't feel the need to leave your video on as well. Davis and I will be turning ours off as well during the webinar to focus on our presentation. Now, our presentation is very special. When we look for someone who's able to talk about decarbonization inside of IDEA, there's a very, very large range of people that we can speak from, and we're very lucky to have Martha here with us today. She actually presented this decarbonization effort at a previous IDEA that I got to attend. And for me, I have to hear it a couple times to learn it. So I really appreciate Martha coming and telling us about her decade-long experience of decarbonizing Carleton College in Northfield, Minnesota. So without further ado, please welcome our guest host, Martha.
Thank you, Chase. And Chase, I'm so pleased to be here today and to see some familiar faces on the webinar. I have been participating in IDEA for probably 8 or 9 years now, as an owner initially, and now on the consulting side. So a couple of different views there. And I'm going to share, as they pointed out, my experiences with decarbonization at the 101 level. And hopefully what we can do too is point some of you to ways that you can get more involved in this or learn more through other IDEA forums as well. So we'll just get started here. Who am I? Where have I been in my trajectory here? I do have an engineering degree. I've always served in more of a project management role though, first as an owner's representative, and then the last 12 years, as Chase pointed out, at Carleton College. Carleton College is where my career took a real turn towards sustainability. I had been working on lead building projects and kind of aware of climate issues, but about 12 or actually now 13 years ago is when my career actually started to focus primarily on sustainability and climate. What does an energy manager do at a college? Just to give you a brief overview, they manage the energy, both the data, the meters, the utility billing, the procurement of utilities, the energy conservation projects, etc. In my case, I also managed capital projects because I came from that background. And so here's a wind turbine that we put up in 2011 that has been providing the campus with 30% clean energy, clean power since then. And then, as we'll talk about, a utility transition was another big project for me, from steam to hot water and geothermal. And then I also managed a lot of this campus sustainability program. So the cultural piece of this about food and waste and sort of individual actions. So that's a whole different layer, mostly not anything to do with engineering, but more about people and people's behavior. So I'm going to start with just what is decarbonization, because I don't know where everybody is at, and you've certainly heard it as a buzzword, but what does it really mean? We always kind of think about this as the fact that the Earth is a very, very, very unique planet. And it's very unique because of the balance that it achieves between the greenhouse gas emissions or carbon dioxide emissions that are going into the atmosphere, and then those that are being taken out of the atmosphere. And it's a very well-balanced cycle. And as you may have heard, with the last century or so of humans kind of adding more on the putting in carbon to the atmosphere side, that balance is disrupted. Here's a graph, the brown line showing parts per million, which is the units that we use to measure carbon in the atmosphere. And it had hovered around, 280 or 250 for quite some time. And in recent history, basically since mid 20th century, it has taken a sharp turn upward. And that's the concern here, is what does that mean when the atmosphere has more carbon in it than it can take out, than the Earth's systems can take out. What you see on the right here is a NOAA carbon climate model. There are climate models that are getting better and better and better at predicting what this means and what might happen. And these are the types of things on the left here that we might see. And some of these might be good. It might be good in Minnesota, where I live, to have a longer growing season and get a little warmer. But I think the focus of a lot of the science right now is what might happen that would be not good, and how do we prevent that from happening. So here's a list of things, to do with precipitation, changes in ocean temperature. If there are more algae blooms, then those ecologies can be thrown off, species can die or need to migrate. So it's just sort of a lot of chain reactions. And this is a webinar in and of itself. So we won't go deep into that today, but it's why people are concerned about this. What does it mean for people? It means that it might change where we plant food and how we get food. It might mean more flooding, especially in low-lying areas, and more often, more frequent, more extreme weather events. So how have we defined this problem? The International Panel on Climate Change defines it as a change in temperature, average global temperature. And they basically have mapped out a number of scenarios where we enact policies that are more aggressive than they are now, or we stick to the policies we have, or we start to roll back policies. And the goal that the models that are most well developed are, what does it look like with 1 degree of Celsius of change in average global temperature, 1.5 and 2. And things start to get pretty chaotic at 2, which is why that's been kind of a focus as to how do we keep carbon emissions or global temperature, average temperature change at or below 2 degrees Celsius. And then again, with defining carbon emissions, carbon is really kind of a index. Greenhouse gas emissions actually consist of many emissions, the 6 that you see here being the most common, and they are often normalized into carbon dioxide as being carbon dioxide equivalents. It's kind of like when we take kilowatt hours and we make it a BTU so that we can add it together with thermal energy. We have to normalize the units. So carbon dioxide is used as kind of the normalizer, which is why you sometimes hear the confusing interchange of greenhouse gas emissions and carbon emissions. People talk about both the same way. The 3 scopes here are very important because that kind of defines the problem statement. Scope 1 is emissions from fuels burned on site. For a campus or a district energy system, it would be the heating, fuels you burn in your heating and fuels you burn in your transportation vehicles. Scope 2 is upstream emissions. So at a campus, you often buy electricity. So the emissions are produced upstream, not on your campus, and that qualifies as Scope 2. And Scope 3 is indirect emissions associated with activities that your organization conducts: air travel, commuting, waste. It's all the activities and the emissions associated with those activities. So today we're going to focus not so much on Scope 3. That's a whole different ball of wax to talk about waste and airline and travel. This is a diagram that looks a little confusing at first, but I brought it up because it's a common way to illustrate solutions to carbon emissions. So the black line on top would be the projected growth of emissions for this particular facility. The dotted line, the black line kind of going straight down, is the ideal path to 0 emissions for this organization. And then each of the solutions that are being proposed has a projected amount of carbon reduction potential. And those get mapped up as these wedges to sort of map out over time how you might reduce your carbon footprint. So that's kind of defining in a very, very quick nutshell what the problem is. Now, how do we think about the solutions? Because it is a pretty nasty, complicated, wicked problem. This is a pretty common representation of the pillars of decarbonization in a very, very, very small nutshell. So there's a lot to say about each of these, but certainly we want to get more efficient. The more we can electrify, the more we can tap into zero carbon power sources. And there's many of them, there's hydropower, and we're just coming up with lots of different ways to make carbon-free power. And then remaining emissions, we would sequester them either by sucking them out of the atmosphere with vegetation, organic material like trees, or there have been many proposals to actually physically inject carbon back into the earth. Like with fracking, we've been taking fossil fuels out of the earth, and we would basically re-inject those fossil fuel kind of outputs back into the earth. So there's a lot of crazy, interesting research going on about how to actually physically sequester carbon. But these four things together sort of make up decarbonization. We'll take a little deeper dive now into what those solutions look like. Purchased electricity, which is the most common form of Scope 2 emissions. Again, these are emissions produced somewhere else by somebody else that then that energy gets sent to your campus or your district energy system or your facility. There are many ways to look at this, but not, it's a less complex problem, shall we say, than the fuels that are burned on site. There are ways to construct on-site renewable energy. And as I mentioned, we built 2 wind turbines at Carleton, which dramatically reduced these Scope 2 emissions. And then many of you are probably aware of the fact that you can now purchase green electricity, and I know we've been hearing a lot more too about green steam for people that buy an off-site steam producer, buy steam from an off-site producer. So that would be either just simply paying your power company a little bit more to invest in renewable energy, and then you get to count your electricity as zero carbon. Power purchase agreements are when you collaborate with a developer or an owner of some land that is elsewhere, and you pay them for some amount of renewable energy credits through a power purchase agreement. So you're actually kind of involved in the project, and it becomes a project that would not happen without your involvement. And then renewable energy credits are a market tool. So somebody who you don't know, who you're not involved with, builds a project either to an anaerobic digester at a landfill or a wind farm or a big solar array, and then they can sell the renewable energy credits for that project on the market, and you can buy them usually for pretty cheap right now. Won't always be cheap, but right now it's pretty cheap, and count that as then offsetting your Scope 2 emissions. The other thing is, even without doing any of those actions, either offsite or onsite, you can watch the emissions profile of your own power grid, because they're actually getting, the power companies, the utilities and the operators are collaborating. And right now, the US grid is on average 40% renewable. And that's including hydro, nuclear, wind, solar, and other kind of a sliver of other things like biomass. So carbon neutral or carbon-free electricity is becoming more available just through your provider without doing anything extra. So as I said, Scope 2 options are much more manageable and much more clearly defined, I think. Scope 1, vehicles, as we know, we've seen electric vehicle charging stations popping up. We put in 3 of those at Carleton and 2 in the city. We're sort of partnering in many ways with that. And we now have the Biden administration has asked each state to submit a plan to put a high-speed charging station every 50 miles along the federal interstates. So we're going to see charging stations popping up. We're going to see vehicles becoming more affordable or becoming more available or more popular. And that's really the solution right now for vehicle traffic. There are other options, but the most common is electric vehicles. And now for the tough nut to crack. We're going to spend a little bit of time here. On heating, what we're seeing is heating systems used to run on steam. In about the mid-century, mid-20th century, if you were building a brand new district energy system, you might build it with hot water, because you could pump hot water now. You have a pretty good electrical grid. Back in the late 1800s, the electrical grid was pretty shaky, and so you didn't have a lot of pumping power, but steam propels itself. So it made sense to put steam in a pipe and send it out to 5, 10, 20, 30 buildings. Hot water came along later and became more efficient. The losses in that distribution were much less. And now we're seeing even more advanced solutions like ambient loops, which are even lower temperature hot water. And the lower the temperature, the more efficient, because you have less loss in those lines, and you can also produce that hot water with more efficient equipment up front. So this is kind of a complicated graph, but this is similar to something we thought about at Carleton College for what's this decision on heating, the future of our heating system. And they were facing at the time a lot of decisions about capital renewal, maintenance renewal. So we could maintain steam, and there are a few options for that in terms of equipment, or transition the distribution to hot water. And that could have either been a low temperature solution or a medium temperature, what I'm calling a medium temperature solution. You see those ranges there. Medium temperature, it's harder right now to find really efficient heat pump equipment, but it's starting to emerge, and you're seeing some idea webinars that are talking about that. So keep your eye on that. Low temperature, Carleton College chose to design a system. We worked with Salas O'Brien and McGough Construction to do a system that was aimed at eventually becoming at 100% 120 degree Fahrenheit hot water for heating in Minnesota. So we can talk more about that in the Q&A, how that worked. But again, as you see, here's another way of displaying this. When you move to these lower temperature hot waters, what we'd call low temperature hot water, maybe between 120, 140 degrees, or ambient loops, which are even lower, there are many, many, many more very highly efficient equipment options available. Now, that's not to say that these aren't developing for higher temperatures, but this is why you might be seeing presentations at IDEA that are these massive transitions from steam to hot water, and not just any hot water, but low temperature hot water. Why do we do that? You can see here, look at the green dots, which are how much energy you're putting in, to how much energy on the red dots that you're getting out. An electric boiler gives you a 1-to-1 ratio. You put in 10 dots, you get 10 dots of heat out, or energy. As you move to these more efficient heat pumps, air source and then even water source, you can put in 10 dots of energy here on a water source heat pump and get up to 60 or 70 dots of energy out. So that's a COP of 6 or 7 when those systems are really nicely balanced between heating and cooling. And that's, again, why people are really excited about heat pumps, why they're being incentivized, and why people are actually going so far as to transition entire steam systems to hot water so that they can use very efficient heat pumps. So we'll buzz through a few things about kind of practical steps. If you're an owner or you're thinking about this as an engineer, what are some of the first steps? This is a slide that you will receive from Jason. We're going to send out the slides after the presentation. But I thought to myself, I wish when I was an energy manager that someone would have just told me, what are the top 10 things right now to do that aren't just changing light bulbs, a little bit more advanced than that. We talked about low temperature hot water. It's also about getting steam generation into the buildings, so you're not relying on a centralized steam system, a district energy steam system as much. Building envelopes with new buildings are extremely important just to use less energy to begin with. Shaping up the metering programs, doing those easy energy efficient upgrades like it is light bulbs, it's VFDs, it's looking for heat recovery opportunities. Do we have exhaust that we can pull heat from exhaust and re-inject it in the system? It's deeper things like retro commissioning and controls upgrades. It's certainly thinking about this strategic electrification movement. What does our electrical grid look like now? What's its condition, its capacity? Doing that sort of facilities condition assessment is very important as a first step. You could start purchasing green power right away. You could do a high-level energy master plan. Many of you already have one of those, or many of you on the engineering side are already doing these as part of your practice. Sometimes they're called energy master plans, sometimes utility, and sometimes now we're even seeing them called decarbonization plans, and where that becomes a primary goal. And of course, if you're an owner, and if this was the case for Carleton, mobilizing that really, really motivated and enthusiastic team of people to lead the project was a very important first step. You can also think about your goals, and I put this up because everybody thinks of the quantitative goals. Whoops, I think I got my titles flipped here. The quantitative goals: reduce carbon, reduce energy, provide for redundancy. But there are so many qualitative goals as well about renewing systems, having easier staffing requirements that aren't based on a high pressure steam system, aligning with other capital projects that you're doing anyway, and also reducing risk of future energy volatility and carbon taxation, whatever form that might take. The less energy you use, the more you can avoid that risk. And of course, reputation. Many corporations and schools are making commitments, and we're now seeing states making some goals and aspirational targets, but also some requirements to meet. So there's quite a few motivations for doing these projects. And then it's always a beginning of, let's look at what we have going for us that's positive and it's an asset we can build off of, what is not working so well that we want to correct. And these two pictures are from Carleton. We had a brand new electrical grid. We'd upgraded to 13.8 kV. We had 2 wind turbines providing green power and great, this is the diesel backup, great backup, great redundancy on the electrical system. So we knew we could build off that strategic electrification pillar. We also knew we had one of our liabilities was all these 100-year-old steam pipes. Here we are. We don't get many pictures of this happening because we don't want to advertise it too much. But here we are digging up a steam leak. So it's a really important first step. Understanding your energy data and really getting those meters. We just had a thermal and why is it so tricky to meter thermal energy? An IDA webinar. Watch those webinars, get those meters fixed, because this is what becomes the basis of all of your solving, your problem solving. Looking at buildings is really important. And so getting building level meter data, not just campus level meter data. And then understanding how all that meter data overlays, especially heating and cooling. What you see in purple here is the overlap of simultaneous heating and cooling, which is where we can take heat we're trying to reject out of the chilled water system and repurpose it into the heating water system. So that's when we get those hugely high efficiencies, 6 or 7, COP of 6 or 7. This is a heating dominant campus, and I'm very familiar with this type of setting, having done a project in Minnesota. But there can be even more exciting outcomes if you have a cooling dominant campus. Here's one that there's a lot of simultaneous load all year long. And the winter heating or the summer heating can be often domestic hot water or reheats. And the winter cooling can often be data centers, teledata rooms and things like that. So there's always an opportunity to take advantage of the simultaneous heating and cooling. If you do proceed with one of these studies, you're going to start to evaluate lots of different types of technologies based on some of the parameters that you set in your objectives and whether or not you want to actually transition to hot water or whether you already have hot water. We also look really hard at electrical systems because, as I mentioned, a lot of this depends on moving things that were on gas or oil or coal to electricity. So here's a campus electric load profile. You can see in the summer over on the left side, they turn on the chillers. And so that's their peak for the year. Here's what would happen if they tried to heat with an electric boiler, which again has that COP of 1. One unit of energy in gets you 1 out. The heat pump approach here is more like that. So now the peaks in the winter when they're heating with electric equipment are closer to the summer peaks and also below their capacity. So they can manage a heat pump project without having to significantly upgrade or increase their electrical capacity. And when all said and done, many technologies can be layered in to provide these different heating and cooling load profiles with what they need. We're always looking for key performance indicators. And I always say this is a 3-legged stool. It's really easy to always look at cost. Is this going to pay back? What are we investing and what are we going to get? But energy and carbon have to be part of that equation as well. So looking at how much carbon we can save, how much energy we can save, and the cost of the projects. So here's a quick run through of the Carleton project, and then we'll stop for a little Q&A and discussion. Carleton is a smallish campus, 2 million square feet. It has about 50 buildings, maybe 35 or 30, somewhere between 35 and 35 and 40 are connected to the district energy system. As you mentioned, they already have wind turbines. They had some solar. They had some solar thermal on rooftops. And what they ended up doing was transitioning all the heating from steam to hot water, putting in 2 vertical bore fields. Here you can see 1 and 2, and 1 horizontal bore field, geothermal bores, and placing the new heat pump to serve those geothermal bore fields in a new science building, which you see right at the middle here. And the aha moment for our engineering team from Salis O'Brien and for Carleton College was, we're building a new science building. We're going to dig a big hole. If we dig that hole 1 level deeper, we can get a new energy plant, start building the new energy system while we're still running the old one, which is over here on the left. So there's some strategic implementation and phasing that had to happen to make this whole thing work. Here's what that energy load profile looks like, bar chart instead of a line graph, but You can see in the old system, the heating and cooling were completely separate. In the new system, which is below, the yellow is all that time when the heating system or the chilled water system is just putting heat directly into the heating water system, maximum efficiency. The light blue and light orange are when we're drawing from the bore fields. And there's still some gas boilers in the dark red, topping it off in the winter. And the existing chillers, which we already had, electric chillers, in the dark blue on the bottom. So what it shows is a hybrid system. It's not all geothermal, it's not all renewable energy, it's not zero carbon, but it's really a strategic approach to optimize these different pieces of equipment for when they're at their best and highest use. For Carleton, this project had a break-even point on cost because the boiler operators who had to work 3 shifts because we had high pressure steam now only had to work a day shift. And they liked that, and we liked that, and it saved a lot of money. So you can see the bump in green at the beginning is capital costs, and then it flattens out quite significantly because the operating costs for the maintenance, the O&M, and the staffing were so much lower. And again, this shows just on the left that there are some utility savings, but because electricity is more expensive per BTU where we are, and most places, the utility savings ended up being about 10%. The maintenance cost is where we really saw the savings for this particular project. And again, it had a significant reduction of a significant impact on the carbon footprint of the college. The first 2 drops here are the 2 wind turbines. And then you see the last drop is transitioning from steam to hot water and from the old high pressure steam boilers to mostly a geothermal heat pump, 70%. The EUI for the campus, which used to hover just over 100 kBTUs per square foot, is now somewhere around 50, if not even below 50. So the EUI, the energy use intensity of the campus, is less than half of what it was, which means the campus uses less energy and is exposed to less carbon taxation and energy volatility as a result. So that's a quick case study. And I think we wanted to leave some time for questions. So I'll leave my slide up here for a bit. Anybody that wants to write down my email address can feel free to ask questions later. But Chase, do you want to get started with the Q&A?
Yes, so just if you have a question, the Q&A icon at the bottom of the Zoom meeting is where you can enter that question in, but I'm going to take advantage, and I'm going to throw the first one to you, Martha. On your slide of available technology for low temperature hot water versus ambient, the same equipment was available for both, and I'm just curious, what are some of the advantages of using low temp hot water over ambient water, I guess, for campuses?
That's a great question, Chase. So an ambient loop is something where you actually don't have a separate heating and cooling loop. And there are people on this call that are probably more qualified than me to answer this, but what it really means is that you're changing the whole structure of the system. So not everybody can do that. If you're dealing with an existing condition where you have separate chilled water and separate hot water or steam, it may not work for you. But it will have a heat pump at a central location that heats the ambient loop up to some temperature between 70 and 100 degrees Fahrenheit, let's say. And then in each building, you have a second heat pump, which will then boost that temperature higher to the point that the building needs. And so one advantage is that you may or may not have to modify your building heating systems quite as much. But all those pros and cons have to be sort of weighed. The other thing is, if you have an existing building with an existing mechanical room, there may or may not be room to put that booster equipment in there. The low temp hot water is really, I think, more of a traditional model where you're just lowering the temperature of your heating water loop, and you're still having a separate chilled water loop. And so all that is done with equipment at the central plant. The disadvantage to that, or the challenge with that, is then whatever temperature you're running at your plant, you have to modify all of your buildings to be able to operate at the temperature you're sending out from the plant. And so at Carleton, what we did was we had the east and a west, and on the east side, we converted all the buildings to operate at 120 degree water because those buildings were already slated for renovations, or the modifications were manageable, meaning we could find ways to kind of shortcut and do things that would work that weren't full building renovations. We left the west side running at 180 degree water, the heating of the buildings. And so in the winter, Carleton does split their loop into a 120 side running off the heat pump and a 180 side running off of boilers. And then spring, summer, and fall, it can all be connected because it can all run off that lower temperature. I would consider that a phasing solution, because eventually those west buildings will get renovated more deeply. So it's a long answer to a short question, but the choice between the two is going to depend on what your existing conditions are. If you're building a greenfield site, an ambient loop is a really clever solution. And it's very, very efficient. That's the thing, is it really pushes the efficiency, the lower you can be on your hot water temperature. But if you're dealing with an existing condition, that may or may not be an option.
Thank you.
All right, thanks, Martha. So we have a question here in the chat. How are the projects at the college funded? And was there some kind of revolving fund there for the campus?
That's a great question. So that project was a combination of funding. There was a bucket of money that we called the decarbonization budget. There was a bucket of money for capital projects, which are those renovations I talked about that were already slated. And those were usually buildings that were using still complete steam radiators, completely steam. They are the oldest buildings and they needed to be renovated anyway. What we did is we accelerated the timeline for some of those renovations. So they were funded out of a capital budget. And then there was a maintenance budget for things like controls upgrades and air handling unit replacements. And so we tapped the maintenance budget for portions of the scope. So we've started with these 3 different buckets. And then within the decarbonization bucket, we had some operating reserves that we set aside, and we sort of funded chunks each year from the operating reserves. We financed a large piece of it because we were already financing the science building construction, and we rolled all that together. It was at a time when rates were quite good, in around 2016. And then we did, as I said, we did siphon off some maintenance money, because we were basically, by renewing the system, taking a lot of deferred maintenance off the list. So the maintenance department was getting a huge amount of deferred maintenance crossed off the list. And in exchange, we peeled parts of the maintenance budget each year to supplement that decarb funding bucket.
Thank you.
Our next question, was there any process steam demands on campus? And how if there were, how were those met with the new system?
There were, and there always are. That campus had dining equipment, kettles, steamers, dishwashers. And so in the dining facilities, we installed, in one case, an electric boiler, in another case, a gas boiler that produced steam in the basement of those buildings. So instead of getting the steam from the central plant, which is what they used to do, they got it locally in the buildings. We had humidification, which we sometimes made, I think in all cases, well, some of them were gas, electric humidification at the point of use. And some of them remained gas. Again, we did this sort of strategic approach where we didn't say zero gas, zero fossil fuels. We said strategic use of fossil fuels where we have to and where it makes a lot of sense. There was something else I was thinking of. Oh, domestic hot water. We had campus steam heat exchangers on domestic water tanks. What we did is we went to a tankless solution. So now the campus hot water comes in at 120 degrees. There's a plate and frame heat exchanger. And on the other side, the domestic water for that building gets heated up to something like 118. And it's constantly circulating. And they are testing it so that they're maintaining water quality. But we got rid of the tanks, which were really, really gross. I'm glad they went away.
Thank you. So I actually have a question. So you mentioned that it was quite a process going through kind of the 120-degree transition. Sounds like you've converted some of your buildings. I know a lot of times when we've kind of gone through this, a lot of the heating coils are oversized enough where you can go to a lower temperature. But going from say 180 down to 120 is, that's quite a jump. You have anything that could give you a kind of a sense of scale, like how many buildings required more of a wholesale renovation versus say just a plug and go, like you might do if you had say a medium temperature water loop?
Yep. The buildings that had mostly perimeter radiation for their heating, which were a lot of our dorms, they didn't have they didn't have cooling at all, most of them, and they didn't have a ton of ventilation, just kind of the bathroom air ventilation. So In those buildings, the radiators came out and they were replaced by panel radiation. Runtal and Meissen are two common brands, but what we were able to do is instead of having sort of a 4x4 or 6x6 fin tube going under a window, we now had a panel radiator kind of wall to wall and from floor to the windowsill. So it gets bigger, but it looks nicer and it blended in nicely with the wall. I was relieved about that. In buildings that were mostly airside systems, our engineering team was very conscientious about addressing what you just suggested, which is, are there, the VAV coils, are the air handling unit coils, is there anything that's oversized enough that we can actually make this work? When we couldn't, sometimes we could use the cooling coil as a supplemental heating coil. And other times in the air handling units, we had to replace the coils with larger coils. And our coils were steam fed. So we also had to redo the riser piping to the coils. Sometimes we could do with VAV boxes some close looks at the controls and how we were controlling to the discharge air temperature. And so that allowed us to not replace VAV boxes wholesale. We could do some controls changes. So I think it's really important. It's not something you get in a high level study. When you're at a concept level, you might have to assume the worst, or at least the almost worst. But as you can get into the design development and construction documents, and as your team really looks at all those coils, the hope is that you'll find some things that were oversized or places where you can make those decisions about using a cooling coil or adjusting controls. And lastly, we kept a cold spot watch list. The maintenance department and I said, let's take the chance on this one. Let's take the chance on these VAV boxes, or let's not put a radiator back in that interior bathroom because we don't think we needed it to begin with. And then we made a list so that we could later go back and retrofit if we were wrong on our assumptions.
Thanks.
Mm-hmm.
I have an additional question. So I saw on the overlay, you had 3 geothermal fields at Carleton campus.
Yep.
And you got 70% reduction of your carbon use. Is there plans to add a 4th one to further reduce the carbon footprint there?
That's a great question. Carleton has continued to think now about, the way that heat moves and heat recovery and where can they get more heat. There might eventually be, there's not a plan right now, but the latest development, again, they kept Salis O'Brien on board for their next piece of utility work so that we could kind of continue that thought process. And with a residential housing development, the idea was perhaps we could, instead of having a bore field, tap off of the potable water line that goes to the water tower because it was passing right by the site, and install a heat pump that could take advantage of that continuous stable temperature for both heating and cooling. So it's that type of decision and that type of a switch in the mindset of, instead of just throwing in another boiler, hey, is there waste heat somewhere or some sort of constant temperature, wastewater, running water that we could tap off of to get free heat before we have to make new heat? Just by moving that heat around, we might be able to get some free heat before we have to boost it to the desired temperature. So I think there's not a plan now, but that frame of mind is now there about the future and how to expand that use of free heat.
So here's a question from the Q&A panel is, see electrification being a big part of the decarbonization plans for many campuses. What are some of the challenges that you see with electrification kind of moving forward?
I love that question because we just put an article together for the next District Energy magazine that answers that question. And I'll give you the preview today, but one of the challenges is certainly the aging grid and upgrading the grid, just like we've done on campuses where many campuses still are, and many were at 4160 volts, and we've pumped that up now to 13.8 kV. It seems to be kind of a common trend. The grid itself needs that type of holistic upgrade. And it can be very difficult to permit those projects because they cross state lines, even though they're federally regulated through they're federally regulated, but the permitting happens state by state. So that's a challenge. Another challenge and opportunity is integration of what they call smart grid, but it's really advanced controls that look at bidirectional flow of electricity. So they're not just looking at how much demand is out there and I, the utility provider, I'm going to send it out to you. It's also looking at how much is being produced at distributed generation sites on your roof, at your house, or at this wind farm, and getting really much more precise about balancing the bidirectional flow and then using battery technology, maybe even electric vehicles as part of that interactive grid. And then another challenge and opportunity is energy efficiency. I think there's a lot of room still for energy efficiency that can be moved forward. You'll see, though, again, a lot more in that IDEA district energy article. And then I think this topic of strategic electrification is going to become much more a part of our IDEA world in the coming years here.
Agreed. Thank you.
All right, that was all the Q&A questions we had. Does anyone else have any additional questions for our amazing presenter, Martha? All right, Davis, you want to start with a little bit of a wrap up here? Definitely want to take a moment to thank Martha for her time putting this presentation together. We really appreciate your discussion topic.
Thanks for the invitation. I'm happy to get more conversation going about this.
Yes, thanks, Martha. So just kind of reminder to everyone as we wrap up, keep the conversation going through all the IDEA forums, and of course at campus, not campus energy, IDEA annual coming up in Chicago in a couple weeks. For the YPG side, we're going to be launching kind of our first of its kind of a District Energy 101 workshop. It's going to have very similar to this, kind of real entry-level, high-level information on a lot of the different topics that you would see out there, really designed to kind of get you engaged, especially some of the people who are earlier in their career. A lot of them might be even already experts in their own segment. So someone from Train might already be an expert in chill water, but they want to know more about steam, heating water, decarbonization. So we're looking to do kind of a real entry-level targeted, especially in those first couple years, people and some of the first-time attendees. This is going to be a kind of a free workshop scheduled on Monday before the opening of the exhibit hall. And the topics are going to be chill water, steam, and power generation. One of the presenters is going to be our very own Chase Doobie. So make sure you tune in. I told he may wear his hat, he may not. Depends where the screen is.
Well, we'll keep the surprise and the anticipation building. So, like Davis said, my backbone is in power generation. So I'm happy to share my knowledge. It won't be a boring presentation with me. I can't speak for chill water or anyone else for that matter, but please come and join us. I think it'll be very helpful, especially for our young professionals. And of course, afterwards, we'll have the YPG forum. And if you don't land in time, you don't make it in time for the 101, you are still very much welcome to attend the YPG forum that happens before kickoff as well. We're always welcoming our young professionals to meet with us. You see a friendly face, you get to know someone beforehand, then you see them in the hallway the next couple of days. You talk about maybe some things that you've learned, some highlights. So definitely have that conversation, that connection. And as you see different things, if there's something you would like to hear more about, or maybe an idea for the next webinar, please reach out to myself, to Davis, and let us know some of these ideas of what you would like. And there's the famous cowboy hat. Davis is smiling right now. So it may make an appearance in Chicago. It will certainly stand out. But there's our email addresses. Feel free to send us your thoughts on ideas for our next webinar, or maybe even after 101, if you have an idea of, hey, can we try this next time? We're very open, very responsive to our YPG members. So please feel free to share some thoughts with us.
I think with that, we'll wrap it up. Thank everyone for your time today, and hopefully we'll see you out there at IDA. Take care, everybody.